Hello, everybody. This is Jack C. And right now we're going to discuss a new paper that I just found, and it's pretty cool. And it's all about trying to get graph neural networks to be more accurate with limited label data. And the trick here is to use knowledge distillation from language models. And yeah, And what I like about this paper is that it does it in a way that the method actually works, right? So typically, when you try to get data for a graph neural network, there isn't much data out there compared to vision tasks and language modeling, right? And typically the amount of data that you get for graph processing is around like a few thousand. So yeah, it's a pretty challenging task right there. But if we can somehow use the large language models to help the graph neural network out, that would be a really good solution to our limited data problem, right? And without actually going in depth into the methods, if we go straight into the results, it is actually quite promising here. So as you can see, right? Okay, right. So obviously, this is their knowledge distillation approach, right? And they have performed a lot of controls here. For example, if we compare the GCN on on its own, right, it only achieved below 50% accuracy, sometimes higher than 50%, sometimes close to 60%, and it depends on how many shot you use during the prediction process, right? And if you compare it with their approach, right, which is this one right here, if you equip it with Llama, Gemini, or GPT, the accuracy actually improves by 2% or more. And as you increase the number of shots, the the accuracy just keeps on increasing, right? So typically the accuracy improvement is around from 1.6 up up to 3.9% roughly. So this is telling us that their approach actually works, right? And if we and the same is about the same for another different data set called core, right? All their essentially it works, right? It works. That's the point right here. From 60% to 70 plus percent, right? From 72 to 73, and from 65 to oh sorry, sorry. I got that wrong. My bad. Uh, Dang it. Let me see. Yep. From 72 to 75%, and from 72 to 78%. And the accuracy just keeps on increasing, right? And it increases to the point that it even outperforms the other models as well, right? So so let's have a in-depth view of this paper, right? And because it works, therefore we should go through it in depth. And this is something that you and I could potentially use it for our own research, right? Or maybe for your own personal project if you're into that. Okay, so let's start off with the abstract here. Okay, grabs are used a lot in the real world, including social network analysis, bioinformatics, and knowledge graphs. Graph neural networks, GNN, have great ability in node classification. Okay, so they're focusing on node classification here. Got it. Right. Okay, unfortunately, GNNs is kind of bad with few label nodes. Despite the prevalence of few-shot node classification tasks in real-world applications. And now to us that are not so sure about what few-shot classification means, not to worry, because we're gonna ask ChatGPT here, right? And bear in mind, this is my first time reading the paper as well, so I will be learning the same paper as with you guys here. So let's have a look. So what's a few-shot node classification? So it's a machine learning task where you will have to classify the nodes in a graph using a limited number of labeled examples. So it's a few-shot setting. In this case, I would assume that the number of shot corresponds to the number of training example that you have from the task right here. So for example, we can ask, what does 5-shot mean? Yeah, in this case, 5-shot would refer to 5 labeled examples per class to learn from. So if we are talking about 5-shot node classification, then you would have 5 label nodes per class that you want the model to classify. So that's good to know. Okay, so to address this challenge, there's a lot of approaches, including graph meta learning, transfer learning, and methods based on LLMs. However, traditional meta learning and transfer learning often require prior knowledge from base classes or fail to exploit the potential advantages of unlabeled nodes, right? So basically, it failed to exploit unlabeled pre-training, something like that, right? So meanwhile, the large language models may overlook the zero-shot capabilities. Overlook. What do they mean by overlook? I don't know. And rely heavily on the quality of generated context. Okay, and it relies on the generated context. In this paper, we propose a novel approach that integrates LLMs and GNNs, leveraging the zero-shot inference and reasoning capabilities, and employing a Graph-LLM-based active learning paradigm. Okay, right. So here, active learning paradigm to improve GNN's accuracy. Okay, what do they mean by active learning? Well, active learning is a bit complicated, right? But we can always ask, right? So active learning is a method that aims to improve the accuracy of the model by selectively querying the most informative data points to label rather than using a random exhaustive sampling approach. So so the goal of active learning is to minimize the amount of labeled data required while maximizing the accuracy. All right. So how does it work? Right. So roughly, step one, we start with a model that is trained on some small initial labeled data set, and after that, all right, the model identifies which unlabeled data point would be most beneficial for learning. This is done using a query strategy or acquisition function. And next, the most informative data points are sent to the human, basically to the annotator, right, to label, right? So the human has to label that, right? And after that, the newly labeled data is added to the training set and the model can be retrained. So steps 2 to 4 can be repeated until the performance reaches an acceptable level of accuracy. So it's more of a smart way to make use of the limited data set that you have, right? So with that, right, this is their approach, essentially, graph LLM active learning. So let's actually do this. So this is GNN plus LLM plus active learning. Okay, actually, they should use this term right here, active learning, in their title, because that's what it's about. Okay, what I would like to do now is to actually go to the conclusion. Right, okay, right. In conclusion, they say, in this paper, we extend the task of node classification to a more challenging and realistic case where only a few labeled data are available. Right. To tackle this challenge, we propose a novel few-shot node classification model that leverages zero-shot and reasoning capability of LLMs. Right. So essentially, LLMs are as teachers to teach the GNNs from two different perspectives. Okay. And now this is crucial in my opinion. Two different perspectives. Right. The logits from the distribution side and enhance rationales from the feature side. Okay, so there's the distribution side and the feature side, right? Well, okay. Moreover, we propose a Graph-LLM-based active learning approach to further improve the generalizability of GNNs with a few available data by actively selecting and distilling knowledge from LLMs. Right, so they are doing this right here, actively selecting and distilling knowledge from LLMs to assess. Yep, so they have done a lot of experiments on tree citation networks. The evaluation results demonstrate that their approach works the best. Yep, essentially, and we saw that in the result already. So yeah, it's pretty good results. But now what we're gonna do is to actually go through the introduction quickly. So okay, let's see. All right. Graphs are recognized as important data structures. They are pretty cool, blah, blah, blah. Graph neural networks are really good in modeling, right? But they kind of suck when you don't have enough data, especially for node classification. Oh yeah, they have a typo here. Node representation. Yeah, so this is node representation. Yeah, node representation learning. Due to various reasons such as labeling costs and privacy issues. And I think that's applicable to social networks, but who knows? Yeah, one would need to train a GNN classifier with sparse labels, and this is called few-shot node classification. Blah, blah, blah. Yeah, so training on web documents can be costly, blah, blah. Consequently, when confronted with such datasets, GNNs may exhibit poor generalization on unlabeled nodes. To tackle this few-shot problem, there's a lot of approaches, but they require substantial amount of nodes, right, or require auxiliary labeled data to provide supervision. So, and here some people have used LLMs as annotators, right? As annotators, okay. And people have demonstrated that LLMs can help GNNs by generating information from a different perspective. But yeah, and here's what they say, right? But they typically treat LLMs merely as annotators or generators, overlooking their untapped potential, such as the capacity to uncover hidden insights within the results and their zero-shot reasoning ability. Okay, so what they're missing from the LLMs, right, is that they could have actually tried to get hidden insights within the results using their reasoning capability instead of just annotating those notes. How about if you get the reasoning thoughts from the LLMs when they're doing that classification task, right? Yeah, at least that's what I interpret from this paragraph right here. Okay, so in this work, they introduce a few-shot node classifier that enhances GNN's ability by actively distilling knowledge. Okay, so they're saying here, actively distilling knowledge from LLM. Right, so unlike other approaches, they use LLMs as teachers, right, basically relying on their zero-shot inference and reasoning capabilities, right? But they say there are two main challenges. Firstly, LLMs cannot consistently deliver accurate predictions for all nodes. This is just hallucination, right? So how to select nodes that LLMs can provide high quality labels that can benefit the GNN the most, right? So we have a selection process going on here. And number two, how to effectively, right, how to distill the knowledge from LLMs to GNNs. Okay, so with that, they propose an active learning based knowledge distillation strategy that selects, okay, here's the juicy part here. So it selects valuable nodes for the LLMs and bridges the gap between the LLMs and the GNNs. Okay, so and they use LLMs as the teacher model and use it to perform unlimited training data, generating soft labels. Okay, so it generates soft labels for the training nodes along with logits and rationales. So here's the important part, logic and rationales. The inputs are used to supervise GNNs in learning two things, probability distribution and feature enhancement at the embedding layer. Okay, I'm really interested about how they do this now. Okay, in this way, GNNs can learn the hidden information from unlabeled nodes and the detailed explanation provided by, so it includes the explanation provided by the LLMs, which is something that the GNN doesn't have, obviously. So, okay, furthermore, we introduce a novel Graph-LLM-based active learning approach to establish a connection between those two things, which effectively select nodes for which the GNN failed. Okay, right. So select nodes for which GNN failed to provide accurate pseudo labels, but LLMs can offer reliable pseudo labels. Therefore, each of them help each other out. Okay, so the selected pseudo labels are merged with the true labels to train the final few-shot node classification model. Okay, so this approach is actually quite good. I like it. Oh wait, sorry. Yep, sorry, my bad. Yep. So yeah, so let's go through the methods now because I don't want to wait anymore. Yeah. So okay, let's see right here. All right. So let's take a look at the figure here. So initially, if I'm not mistaken, start off with an input graph. Okay, and we have some labeled nodes, I believe, and a rationale prompt and a soft label prompt. So feeding that into the LLM, and then it says, let me see, let me zoom in. Okay. Based on the information provided in the paper, it can be categorized as rule learning. The paper primarily focuses on integrating blah, 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 blah. The emphasis on role acquisition and use of specific programs aligns with the characteristics. Not sure what that means. Oh yeah, so the LLM essentially creates the thought from the rationale prompt, right? And I think it has to be specific to the task, I think, or is specific to the node. I'm not so sure. Okay. And then the soft label prompt, feeding it into the LM to generate a distribution of the logits, right? and then, sorry, yeah, and then, okay, this rationale enhanced explanation gets fed in here, and the logits gets fed in into this LT loss function here. I assume it's the teacher loss function, maybe, right? And let's say, and the GNN, and this part was the GNN, I think. Selected nodes with pseudo labels. Not so sure what they meant here, but let's continue anyway. It's kind of like teacher student and then plus, and then some kind of a LF loss term here, and then undergoing some kind of optimization to get some pseudo labels, and then active learning, and then applying the pseudo label to some nodes here, and then perform knowledge distillation from the LM to the GNN. Okay, right. I would say the diagram is not that clear, but let's go through the methods a bit more. All right, so let's go. Let's start off. Where's the first part? Okay, I think just in case, right? Just in case, we should probably go through the preliminaries a bit. So, okay, understanding LLM's capability. As the sparse label challenge is hard for GNNs to aim to imbue GNNs with the zero-shot learning prowess of LLMs. Right. So LLMs might be good at classifying certain nodes while performing poorly on other nodes. True. It is important to identify what nodes that the LLMs can provide better pseudo labels with rationales that the GNNs cannot. Right. So yes, so there we go. Okay, the LMs may benefit from various metrics to perform node classification as well. Certain metrics exert more influence on correctness on LLM predictions on nodes, which include degree of a node and homophilic ratio. So these two things are important to represent. OBS just crashed just now, but that's okay. Let's continue. So I think the most important part is actually here, the proposed model. And let's have a quick look on it because I'm going to be running out of time soon. Yeah, so to start off by telling you that, okay, right, if you feed in the text embeddings and the adjacency matrix, you get some kind of a node representation. Right, so this is the node representation from the GNN. And obviously you can predict the class of the node, right, by applying some kind of a softmax operation on it to get your probability vector. So it's basically kind of like the logic distribution in some sense. Anyway, all right. Next, you would like to try to get the knowledge from the GNN, but how do you do so, right? So let's see. Okay, and they have some prompts here, but we shall skip that for now because this is okay. So step one, right? Soft labels and logic generation. So you feed in the prompt and the XI, and I think the XI is the raw text into the LMs, and you create and you put in the prompt, which is basically this entire thing right here. You put it into the LLM, and that gives you the output. And now for step two, rationales for feature enhancements. Well, it's about the same way as well, but the prompt is different, right? The prompt is that the model has to think step by step and explain its decision in detail with respect to the task. So it's not just some kind of a prediction. It's all about rationale, essentially, right? So obviously, with the rationale, we need to convert it into an embedding, right? So we can use sentence bird, right? I mean, sentence bird is a pretty common model that you can use to convert text, phrases, sentences into a vector. So this is what they did right here. And now, okay, and say that since the dimensionality may be different from the GNN, right? It is you will have to reshape the size by feeding the rationale vector into a multi-layer perceptron to get a vector that's the same shape as the GNN embedding, right? So it has to be the same shape as HF, right? And next, distilling knowledge to GNN. So this part right here is the most important part, obviously, right? So let's see. Okay, at first, what I did here, I assume for each node, right? For each node in the nodes, in the set of nodes, first convert the logits, right? Convert the logits into this probability distribution, right? Where C is the number of classes and tau is the knowledge distillation temperature. All right. So okay, that. All right. So right around here. Okay. Yep. And this equation right here, the loss term for the teacher. Right. Okay. The student can learn the distilled knowledge from the teacher by optimizing the following loss. So the following loss is as follows, right? So LT equals to some kind of summation term right here, right? And times log Zij, where Zij is the probability that Vi belongs to class J. So that's that. And that's that LT equation right there. And step 2, we have another loss, but this time it's for matching up the feature of both models. So, okay, they have this equation right here, LF, right? LF. So presumably you want to minimize the distance, right, between the GNN node embeddings and also the rationale embedding from the LLM. So that's essentially that. And now now time for objective function of proposed framework. So the student model computes training loss between predictions and label or pseudo-label data. So I is the indicator function which outputs 1 if yi equals to c, otherwise 0. Vs is the set of label and pseudo-label nodes, where and yi is the label or pseudo-label of vi. Okay. With the knowledge distillation from LLM, the final loss function of our proposed model can be formalized as this. So obviously, when you're trying to train the entire thing, you're going to need to do some hyperparameter search to see whether or not the numerical values of alpha and beta is going to affect the model training accuracy as well as its test accuracy, essentially. So, okay, so that's interesting, right? But now here comes the active learning part here. And now the active learning part. Okay, so what they essentially try to do here is that they want to select B nodes for each class where the GNNs has low confidence in the classification score. Low confidence, I would think that it would probably meant by like, you know how when you try to like classify something, there is like a probability distribution in terms of what class that label the model thinks it would be. It would have some kind of like percentages, right? So if there is like a flat distribution, right, that would mean low confidence, if I'm not mistaken. So if something like that happens, then we can ask the LLMs to provide to help out by offering some kind of pseudo label, right? So okay, so there's a lot more here, but I don't feel like going through this part right here. Okay, so, and the idea is that a node is more informative when it can greatly change uncertainty within its neighborhood. In other words, more changes in entropy means the more important a node is. So obviously we're not going to be able to understand this part unless we go through the entire passage, but I think that's probably enough for now, right? If you want to know more about this, please do check out the paper by yourself. But I don't think I'm gonna be applying this approach anytime soon, unless I have no choice. Okay, so now let's get into the results, and we pretty much covered a lot of things, but there obviously is some like uh, uh, ablation studies here. I mean hyperparameter search. So obviously, as you include, okay. So what it found, interestingly, is that there's some kind of a pattern here, right? So so it kind of resembles a parabola. As you increase the alpha value, the accuracy kind of increase, but as you increase it by a bit too much, it starts to drop. And you can see the same pattern for each different data sets, Cora, CiteSeer, and PubMed. And the same is also kind of true for temperature in this case, right? And I think it's also the same for beta, right? And so on. So okay, and it also show that by incorporating active learning, the accuracy can be improved much drastically. So overall, the entire paper offers a really good and sensible approach in increasing the accuracy of GNNs with limited amount of data, and it's something that you and I can apply as well, right? So yeah, the results are pretty good as well, I think. So yeah, yeah. So if you like what you saw, please like and subscribe, and I will see you all in the next video. Bye.